In the heart of the sun, a cosmic dance is taking place. Hydrogen nuclei in the form of deuterium are fusing together. This process, called nuclear fusion, is the engine that powers our star. Deuterium, also known as heavy hydrogen, is a special type of hydrogen. It possesses an extra neutron in its nucleus. When two deuterium nuclei collide at high speeds, they can overcome their natural repulsion and fuse. This fusion releases an enormous amount of energy. Understanding deuterium fusion is vital in our quest for clean energy here on Earth. It holds the promise of a future powered by the same process that lights up the cosmos. Every nuclear reaction involves a change in energy. This energy change is quantified by a value called the Q value. Think of the Q value as the energy balance sheet for a nuclear reaction. A positive Q value indicates an exothermic reaction, where energy is released. This is akin to burning wood, where heat is given off. Conversely, a negative Q value signifies an endothermic reaction. In this case, energy is absorbed from the surroundings, like an ice pack drawing heat to melt. For fusion reactions like those involving deuterium, the Q value is positive, indicating a net release of energy. To calculate the Q value for deuterium fusion, we need to know the masses of the players involved. The key participants are the deuterium nuclei themselves, denoted as 2EH. The products of the reaction depend on the specific pathway. One pathway yields helium-3, 3He, and a neutron, N. The other pathway produces tritium, 3H, another heavy isotope of hydrogen, and a regular proton, P. Each of these isotopes has a specific atomic mass, a crucial ingredient in our energy calculation. With the masses of our reactants and products in hand, we can now compute the Q value. The formula is straightforward. Q equals the mass of reactants minus the mass of products multiplied by C squared. Here, C represents the speed of light, an enormous number that reflects the incredible energy stored within the nucleus. By plugging in the atomic masses for the deuterium reactions, we can calculate the Q values for each pathway. These values represent the energy released in each reaction. This energy is carried away by the products as kinetic energy, the energy of motion. The higher the Q value, the more energetic the outgoing particles will be. This has important implications for harnessing fusion energy, as these fast-moving particles carry the potential for power generation.